2.5 miles. That's how deep the average oil and gas well is drilled into the earth. Some go much deeper. Like the deepest hole ever drilled reached over 7.5 miles, or about 12 kilometers into solid rock, deeper than the ocean at almost any point on Earth. And we do this every day, all over the world. So, how do you actually drill a hole that deep? The answer starts with what we're actually drilling for. A well goes after hydrocarbons, crude oil, natural gas, or some mix of both, trapped in rock formations deep underground. Most wells these days actually produce gas, or a combination of gas and crude oil. The exact product depends on the geology, not the equipment. And the process of drilling, the actual engineering of it, has gotten dramatically more sophisticated over the past few decades. Before any drilling begins, you have to decide where to drill. That decision comes from geology, surveys of the rock formations underground, often using seismic data that maps the layers miles below. Once a spot is chosen, a pad is prepared, a leveled, engineered surface with everything the operation needs. Then the rig is moved onto the pad and positioned over the exact point where the well will go. Now, the word moved is doing a lot of work in that sentence. A modern deep drilling rig isn't a single structure. It's an entire facility spread across the pad, with dozens of major components. The derrick, the steel tower most people picture when they hear the words drilling rig, is just the most visible part. Around and beneath it sit the mud pumps, the mud tanks, the drawworks, the power generators, the blowout preventer, the control rooms, and storage racks for thousands of feet of drill pipe. Moving a rig between locations can take anywhere from roughly 30 truckloads for a smaller rig to 100 or more for the bigger rigs. The derrick itself is the tower that handles the drill pipe. Each piece of pipe is about 30 feet long. Larger rigs join multiple pieces into stands. 2 joints make a 60-foot stand on a double rig, and 3 joints make a 90-foot stand on a triple rig. The stands get racked vertically inside the derrick, which is why a deep drilling rig stands as tall as a 10-story building. It has to be tall enough to hold those stands upright. At the surface, the drill string descends from the top of the derrick into the hole. As the bit cuts deeper, the crew on the rig floor adds new stands to the top of the drill string. The rig, as a whole, is a system for continuously extending a piece of steel pipe, miles into the earth. The pipe doesn't cut the rock, though. Something at the bottom of it does. At the bottom of the drill string is the bit, a steel head studded with cutting elements. Bit sizes depend on the section of the well being drilled. They can be as large as 42 inches at the top of a well, narrowing to as little as 6 inches at the bottom. For softer rock, the cutters are tungsten carbide. For harder rock, they're synthetic diamonds, or polycrystalline diamond compact. The bit doesn't blast or hammer the rock. It cuts it slowly as the drill string rotates. And here's the part that surprises most people. The bit isn't being pushed down. The drill string above it, thousands of feet of solid steel pipe, weighs enough on its own to provide the cutting force. The driller's job at the surface is to control how much of that weight rests on the bit. Too little, and the bit doesn't cut. Too much, and the bit wears out fast. Or the well goes off course. The amount of weight applied is called weight on bit, or WOB, and it's one of the most carefully controlled variables in the entire operation. The rotation comes from a top drive, a large motor assembly that hangs inside the derrick and threads into the top of the drill string. The whole unit weighs hundreds of thousands of pounds and travels up and down the derrick on guide rails as drilling progresses. Older rigs used a system called a Kelly, where rotation came from a rotary table on the rig floor. But modern rigs almost all use top drives. They're faster, safer, and give the driller more control. As the top drive turns the entire drill string, the bit at the bottom, thousands of feet below, turns with it, cutting rock and advancing the hole. The combination of weight on the bit and how fast it spins determines how fast you drill. That speed is called the rate of penetration, or ROP. But none of this works without another component that most people would never guess: the drilling fluid, commonly referred as the mud. The mud travels down through the pipe, out through nozzles in the bit, and back up to the surface through the annulus, the open space between the drill string and the wall of the hole. At the surface, the mud passes through shakers, vibrating screens that separate out the cuttings and solid debris. The cleaned mud is then conditioned and pumped back down the pipe to start the loop again. Now, most people, if they think about drilling mud at all, assume it's some kind of lubricant. It isn't. The mud is doing at least 4 critical jobs at the same time. First, it carries the cuttings, the small pieces of the rock formation being drilled, up and out of the hole through the annulus. Without the mud, the cuttings would pile up at the bottom and jam the drill string. Second, it cools the bit. At depth, friction and rock temperatures would otherwise destroy it within hours. Third, and this is the part most people miss, the mud is creating hydrostatic pressure inside the well. The column of mud, from the surface down to the bit, has weight. And gravity acting on that mass creates pressure inside the well. The taller the column of mud, the greater the pressure at the bottom, meaning deeper wells naturally have higher hydrostatic pressure at the bit. This pressure pushes outward against the walls of the hole at every depth. And it has to. The rock formations the well passes through are themselves under pressure, and any fluids or gas trapped inside those formations will flow out uncontrollably, if given the chance. The mud's hydrostatic pressure has to push back hard enough to keep them from flowing into the well uncontrolled. This is where mud density, also called mud weight, becomes critical. The driller is constantly balancing mud weight against the formation pressure at depth. Too light, and the well kicks, meaning formation fluids or gas flow into the well and increase the risk of a devastating blowout. Too heavy, and you can actually fracture the rock formation and lose your mud into it, commonly referred to as lost circulation. And the fourth job, the cuttings that come up in the mud are the only direct sample anyone gets of what's actually down there. Geologists at the surface examine those cuttings to confirm what formation the bit is drilling through. Here's something most people don't realize about deep wells. The hole isn't drilled all at once, and it isn't a single hole. A well is actually a series of nested steel casings, each one smaller than the last, cemented in place inside the earth, like a telescope made of pipe, miles long. The process works like this. You drill the first section of the well using the largest bit. Once that section is complete, you pull the drill string back out and run a steel casing down the hole. Cement is then pumped between the casing and the rock wall, locking the casing permanently in place. Then, a smaller bit goes back down the inside of that casing, drills the next section deeper, and the process repeats, each casing anchored inside the one above it, each section getting progressively narrower. Each casing has a specific industry name: conductor, surface, intermediate, production. And after the surface casing is set, a blowout preventer is installed at the wellhead to protect the well's integrity as drilling continues deeper. That's not a hole someone drilled in one go. It's a precision-engineered structure of cemented steel, built downward in stages. Why go through all this? Because the rock formations the well passes through have very different properties. Some are stable, others are weak and want to collapse. Some contain pressurized fluids that need to be isolated from the well itself. Some are porous, some are dense. Without the casings, deeper formations would collapse the well from the sides, or contaminate what you're trying to produce, or let fluids flow where they shouldn't. The casing turns the well from a vulnerable hole into a controlled, sealed structure that can be operated safely. But getting there means drilling through some of the most extreme conditions on the planet. Every 1,000 feet down, the rock gets hotter, and the pressure around the well gets higher. At 10,000 feet, temperatures are routinely above 200 degrees Fahrenheit. At 20,000 feet, they can exceed 300. At the deepest sections of the longest wells, temperatures climb past 350 degrees, and the surrounding pressure approaches what would crush most steel equipment ever built. Drilling mud has to be engineered to remain stable. The bit has to function. The casing has to withstand pressures that would collapse normal pipe. The most extreme example is the Kola Superdeep borehole, a Soviet scientific project that began in 1970, with the goal of drilling as deep as possible into the Earth's crust. By 1989, they had reached a bit over 40,000 feet, about 12.25 kilometers into solid rock. They didn't stop because of equipment failure in the usual sense. They stopped because the rock at that depth was so hot and under so much pressure that it was effectively flowing. The borehole walls were closing in on themselves. The rock at that depth wasn't behaving like rock anymore. It was behaving like very stiff toothpaste. There's another problem that gets worse with depth. Bits wear out. A bit drilling through hard rock at 20,000 feet might only cut 1 to 5,000 feet under high temperatures before it's done. Replacing it means pulling the entire drill string out of the hole, joint by joint, stand by stand, back to the surface. A new bit goes on, and then the whole drill string has to be sent back down again, joint by joint, stand by stand, until the bit reaches the bottom of the hole and drilling can resume. This process is called tripping the pipe. And on a 20,000-foot well, a full round trip can take 24 to 48 hours of continuous work. The actual cutting time on a well is often a minority of the total operation. Most of the time is spent tripping the pipe in and out of the hole. Here's a question that took the industry decades to solve. The bit is miles below the surface, inside a hole filled with mud, inside a steel casing, inside thousands of feet of rock. You can't see it. You can't film it. So how do you know what's actually happening down there? How do you know what direction the bit is pointing? What temperature it's working at? What kind of rock it's cutting through? The answer is a pair of tools installed just above the bit, inside what's called the bottom hole assembly. The first is MWD, measurement while drilling. Think of it as the bit's ears. It tells you what the bit is doing: direction, inclination, temperature, pressure, the weight resting on the bit, all of it, in real time. The second tool is LWD, logging while drilling. Think of it as the bit's eyes. It tells you what the bit is seeing. Sensors that measure the properties of the rock the bit is cutting through. Electrical resistivity, natural radiation, density. Together, MWD and LWD give the surface team a complete picture of both the operation and the geology, miles below their feet. But here's the strange part. How do these tools send their data up to the surface? There's no cable running miles down the well. Instead, they send data the same way a submarine sends sonar pings, through the drilling mud column. The tools generate precisely timed pressure pulses in the mud that travel up the column at the speed of sound through fluid. At the surface, sensors detect those pulses, and computers decode them into data. The drilling mud isn't just a hydraulic system. It's also the communication channel between the bit and the rig. And those messages are about to do something even more remarkable. They're going to let drillers steer the bit. Now, most people imagine a well as a straight line, going straight down. That picture is wrong. Modern wells curve. They go down for a couple of miles, and then they turn, sometimes by 90 degrees, and travel horizontally for another mile or two, all underground. A single well can change direction multiple times before it reaches its target. How is this possible? The trick is in the bit assembly. Just above the bit, the drill string has a slight, deliberate bend, typically anywhere from 0.5 degree to 3 degrees off vertical. Depending on how aggressive the turn needs to be, there's also a small motor in the bottom hole assembly, a positive displacement motor, or PDM, that can rotate the bit independently of the drill string above it. If the driller wants to go straight, the entire drill string rotates from the surface, and the slight bend averages out. If the driller wants to turn, the drill string above stops rotating, and only the motor at the bottom spins the bit. The slight bend now points consistently in one direction, and the bit drills in that direction. Using real-time data from the MWD tool, the driller can change the well's path by precise amounts. The result is engineering that looks almost surgical. And modern drilling has changed in another way that matters. On the most advanced rigs, much of the operation is now automated. Computer systems monitor data and continuously adjust drilling parameters, weight on bit, rotation speed, mud properties, to make the operation faster, safer, and more cost-effective. But it's worth being honest about what this actually means. Not every rig is running this way. There are still plenty of rigs operating with traditional controls, run by drillers reading gauges and trusting their experience. The way the job has been done for decades. The fundamental skill of drilling, reading what the rig and the formation are telling you, and making the right call, still lives with the driller, whether the controls are computerized or not. Let's pull back for a moment and look at what we've just walked through. A drilling rig is, in the simplest terms, a system for extending a piece of steel pipe, miles into the earth. But what we've actually built is something much stranger, a precision instrument made of nested steel and engineered fluid, operating blind, in temperatures that would destroy most materials against pressures that would crush most equipment, in formations that behave like solid rock at one depth and like toothpaste at another. We do this routinely, thousands of times a year. Most people never think about where their gas, their plastics, their fuel comes from, but this engineering is one of the quiet wonders of the modern world.